So our next speaker up this morning is Professor Alex Rogers from University of Oxford, who's a professor of computer science. And Alex will be talking about AI for sustainable energy use. So we'll just get set up here and then be over to Alex.
Great. Is there a remote?
Oh, we didn't have a remote. I can do next. If you want to do next slide.
Oh, no. Can I plug in my remote? That'd be much easier. Okay, cool. Brilliant. Okay, great. Thank you for inviting me. So I have sort of two hats in this grouping. So one of my areas of interest is in acoustics. So I do quite a lot of work with open acoustic devices who make the AudioMoth device. So that's a low-cost device for collecting audio in the field. It's used by quite a few ecologists. And one of the things we're interested in there is actually putting algorithms on the device to make efficient use of energy, so deciding when to record, and also just collecting data, which is then typically used in sort of desktop processing to do species recognition and generate insights into biodiversity from soundscape analysis. So that's sort of one area of interest that I work in. The other area is actually energy, so sort of smart grid type work. And I thought I'd sort of talk about that in this talk and describe a project that's sort of been going on for quite a long time, since about 2010, which is monitoring the carbon intensity of the UK electricity grid. So my starting point for this work is basically yeah. So the starting point for this work was 2008 Climate Change Act. So this was the first legislation that committed the UK government to work towards decreasing carbon emissions. So this was very sort of early legislation. I think Mexico had legislated just before, but this was sort of the first legislation around the world that actually sort of forced the government of the day to actually start trying to decrease carbon intensity level or carbon emission levels. And the aim kind of looks sort of relatively ambitious still today. So it's to reduce carbon emissions by 80% relative to 1990 by 2050. And now sort of goals are a little bit sort of more ambitious than that, to reach net zero by 2050 or maybe by 2035. And also at this time, there was a lot of interest in the smart grid. So this is the US Department of Energy in 2009 talking about what future energy systems might look like. And they say, imagine the possibilities: electricity and information flowing together in real time, near zero economic losses from outages and power quality disturbances, a wider array of customized energy choices, suppliers competing in open markets to provide the world's best electric services, and all of this supported by new energy infrastructure built on superconductivity, distributed intelligence and resources, clean power, and hydrogen economy. So some of that hasn't come to pass. So superconductivity, hydrogen economy, probably still a little bit futuristic. But a lot of this it was at the time was sort of calling to computer scientists to get involved in what the future energy systems may look like, and particularly aspects of electricity and information, distributed intelligence and resources. These are all things that resonated with computer scientists. So one of the things I started to do at that time was sort of look at how rapidly technology sort of impacted energy consumption. And if you come to this from a computer science perspective, you can get very sort of slightly blasé about sort of the scope of change that you can realize. So if we look at sort of 2010, when this project was sort of originally kicking off, the increase in energy efficiency of computing was probably a factor of almost 1 billion. We'd made computing hugely energy efficient over those sort of 60 years. But there's something sort of quite striking about sort of information and bits, which doesn't really apply to the real world. So if you look over the same period, the energy consumption of a car has actually sort of gone down in that sort of intervening period. So we drive around with a little bit more comfort and a lot more power. But actually, in terms of energy efficiency of moving us around, it sort of decreased, despite the fact that in computation, we'd had this sort of billion-fold improvement in energy efficiency. So what we started to do all that time ago was to start looking at what the future might look like, and the plan was very clear. We have to electrify things, so internal combustion is very inefficient. We need to electrify cars. We need to electrify trains. You get a double saving from electrifying a train because you don't have to carry the fuel with you. And then lastly, electrifying heating. So using smart heat pumps, which have this sort of magical property that you use 1 unit of energy and you end up moving 3 or 4 units of heat from the outside of your home to the inside of the home, all using electricity. So basically we needed, and the story is still very clear now, we need more electricity and we need to generate that electricity cleanly. And so we started to look at what's the carbon intensity of the electricity that we use. And so 2010 also sort of combined with Apple App Store, and apps were the thing. So we started to look at energy, the carbon intensity of the grid. And one of the sort of the challenges if you start a service or an app is that you kind of have to maintain it. And so 15 years later, this sort of app is still on the App Store. The phones have got much bigger. The app hasn't really changed very much. But actually what's quite striking is sort of how much the grid has decarbonized in that time. So back in 2009, we thought that 336 grams CO2 per kilowatt hour. So this is the amount of carbon emitted to generate 1 kilowatt hour of electricity that's used at the end consumer. 336 was pretty good. And now 246 is kind of middling and not so good. And a lot of the time, the grid is a lot less than that. So what's been sort of striking is that over this intervening period, carbon intensity of the UK grid has dramatically decreased from sort of an average around sort of 500 all the way down to typically below 200 now. And most of that has come about by changes in where we generate electricity. So those fossil fuels at the top, coal and oil, we've never really used very much oil in the UK, but coal was the dominant form of energy generation. And very dramatically, we've stopped using coal over the last sort of 6 or 7 years. Okay, so you can sort of see, going back to 2009, coal was generating sometimes up to 25 gigawatts in the UK, and it's basically gone down to nothing. So there's a few coal power stations which are kept on standby. They may generate sort of a gigawatt of power, a couple of gigawatts, but most of the time they're just switched off. And so this has sort of given the rise to this sort of huge reduction in carbon intensity. Some other generations have to fill in the gap. So in the UK, gas generation is basically following demand, filling in the gap continuously. And nuclear has kind of been declining largely because all these nuclear power stations are getting to the end of their life and they're gradually sort of being switched off. So nuclear generation is actually sort of quite low at the moment, going down to sort of 4 gigawatts or so. And the big story about electricity grid has just been the increase in renewables. So a lot of offshore wind, which has been really significant, and you can sort of see the growth of offshore wind. And now typically on a good windy day, we have about 20 gigawatts of generation on the grid at sort of peak times. And this is sort of quite dramatic. You look at over all of this period, people have been arguing about whether we should build more nuclear power stations and what should we do with the aging power stations, and do we have planning permission to build this nuclear power station? And a single nuclear power station is about 1 gigawatt. And over that time, we've got sort of 20 gigawatts of wind generation that's just appeared on the grid without really anyone sort of being very aware of it. And also solar. So solar has sort of grown, and now on a sunny day, we might have 10 gigawatts of solar power. So these are trends which has kind of happened without really sort of people being very aware of the change. And so over this sort of period since the app launched, in the last sort of few years, people have become very interested again in carbon intensity. And so one of the things I did very recently was work with the National Grid. And what we did was to try and sort of calculate flows of carbon across the grid. So the National Grid Control Center is very used to calculating flows of electricity. They monitor the transmission network, which directs energy across the grid at the level of about 13 large substations. So that's sort of the transmission network. And so what we did was also calculate the flows of carbon across the grid. And then what you can do is you can sort of calculate a national, regional carbon intensity. And this basically sort of tells you a little bit about where traditional generation is. So around the Midlands, we can sort of see the, and South Wales, we've got sort of existing old coal-fired power stations, which are sometimes running. Southwest has a lot of solar. Scotland and the northeast have all of that wind generation sort of being connected into the grid. So they typically have very low carbon intensity. And you can do the same thing at a bigger scale. So this is electricity map. So this is a startup, I think Danish originally, and they do the same thing across the whole of Europe, which has this sort of interconnected grid. So typically in the UK, we might be importing maybe a couple of gigawatts of power from France, maybe from Belgium. There's a Norwegian interconnector. There's a couple of interconnectors to Ireland. And all of these flows, you can do exactly the same calculation and calculate this sort of carbon intensity flow. So these regional maps are kind of interesting because they allow you to think about where might you allocate future resources. So if you're looking to maybe sort of build a data center, you'd look at a map of Europe and you'd think, well, we shouldn't be in Poland because there's going to be a lot of coal-fired power from there. We should probably be in Scandinavia to get sort of nice clean hydro power, or we should be in France with clean nuclear power, and then lots of wind and solar in Spain. So you can use those to make sort of a long-term geographical decisions. But a lot of the trend in here is basically just down to historical accident. So actually, if you sort of live in the Midlands, there's not much you can do. And maybe it's a little bit unfair to think of your electricity as being particularly dirty because this is the national grid, and it is sort of we should share the contributions over the whole grid. So the more interesting aspect is actually looking at time of energy use. And so what's quite striking is that because of the way that the grid is continuously following demand, the carbon intensity of the electricity changes quite significantly over time. So this was just from a couple of days ago, and you can sort of see it at night when demand is relatively low. Basically, the amount of energy that has to be supplied from gas can ramp right down, and so the grid comes comparatively cleaner. And so it's a significant amount of that is the wind generation and the nuclear, and then a significant part of this is imports from France, which is very clean, and then this gas bit at the top, which is just sort of supplying the last little bit of energy. And then as demand increases, basically we end up using more and more gas to meet demand, and so the carbon intensity goes up. And you can sort of see that it sort of plateaus in the middle here because we've got this sort of big lump of nice clean solar power that comes along. That's probably sort of reducing this peak that you would typically be in here. So this peak carbon intensity tends to be towards the end of the day, when not necessarily when demand is highest, but when our solar peak is beginning to wind down. And also depends what wind generation is doing. So this has a lot of opportunity for optimizing how we use electricity. So if the carbon generation isn't constant during the day, we should be thinking about not only where are we getting our electricity from, which supplier, but actually sort of when during the day potentially we should be using it. And lots of loads we have a lot of flexibility in when we actually use them. And so perhaps sort of most strikingly is sort of, we can talk a little bit about the end, is home heating. Home heating is a large consumer of energy. We're typically going to have to use electricity for it. There was a lot of hope about hydrogen for home heating, but that's largely been sort of discounted over the last sort of year or so. So it's going to be heat pumps, and you have a lot of flexibility in when you run your heat pump. You have sort of thermal inertia in your home. As long as you're comfortable, you don't actually care when the energy is being consumed. And so there's a lot of scope for sort of moving that energy consumption around. And the ideal would be to try and sort of probably flatten this curve, try and use energy when it's available. So try and use energy when there's sort of solar peaks or lots of wind, and try and defer energy to low demand times at other periods. So this has been the sort of the dream of the smart grid. The dream of the smart grid is basically to try and encourage demand to follow supply. You know, a standard grid works the other way, where supply follows demand. So if you switch a light on somewhere, a valve in a gas-fired power station opens a bit more steam comes out, and it has to continuously match supply and demand. There's a bit of buffering with some big flywheels, but it really is that responsive that you are controlling these thermal plants just to match supply millisecond by millisecond. And so the dream of trying to match up supply and demand in a more sort of intelligent way sort of comes down to these smart meters. And so going all the way back again to 2010, we were very enthusiastic about the rollout of smart meters. And I don't think even the most pessimistic people 12 years ago would have imagined that 12 years later in 2024, many people still don't have a smart meter. After working in this area for sort of 12 years, I only had a smart meter installed last year, and it really doesn't do very much. It's not the smart device that we were hoping for. It basically just makes a measurement every day and sends it to the company that sends me the bill. But potentially it does hold the promise to do much more sophisticated things. And at the same time, people are very interested in smart heating. Again, this idea that actually heating is the thing that consumes a lot of energy in your home, and having smart controllers would be the way of sort of optimizing it. And for a long time, this hasn't really sort of taken off because we've been using gas in our homes. But actually now with this sort of push towards heat pumps for heating, there is this opportunity to have this sort of vision of a smart home, and actually sort of have the consumption in your home responding in real time to changing carbon intensity. And we're beginning to see companies do this. So a long time ago, we were sort of building all these sort of nice models of what a smart home would look like, with sort of clever algorithms that were optimizing for the thermal properties of the home, changing energy prices, changing sort of local generation. And it's taken a very long time for that to feed into the market. But Octopus in the UK really is actually doing this now. So we have this idea of plunge pricing. So surge pricing is a very unpopular thing for an energy company to sell to their customers. You know, we're going to put the price up at peak times. But plunge pricing is very appealing. It basically means that at certain times, the price is going to go very low. And sometimes the price goes negative. So sometimes Octopus will pay you for using electricity. So if you've got an electric car, if you sign up for this scheme, at certain times you can run outside, charge your car up, and they will pay you to charge your car up. Because all of that grid is, there's too much wind generation on the grid. Typically, they have contracts to buy wind generation. And actually, if you can, if you curtail the wind generation, you have to pay a penalty. So it's better to use that electricity, and sometimes it turns out to be better to pay people to use electricity than it is to curtail the generation. So Octopus is very early days, but Octopus may be this sort of vision of what this smart home could be, and Octopus are very sort of active in exploring this sort of space of AI to build this sort of smart home. And so I've also more recently been sort of working with companies that actually do heat pumps for heating. Typically on larger sites, so typically sort of large office buildings rather than individual homes. There's a certain amount of sort of infrastructure cost. If you're building a heat pump for a large building, you can have boreholes, which tend to improve the efficiency of the system. So this is sort of a live display, which is driven by live data. And you can sort of see there are huge carbon savings. So this is real data using electricity for heating, modeled against a counterfactual if you were just using gas. And you can sort of see that this system is giving a live COP, so coefficient of performance, of 3.9. So for 1 unit of electricity is shifting 4 units of heat into the home. So it's kind of 400% efficient. So it's kind of it's this sort of magical sort of superscalar efficiency. And you can sort of see the carbon intensity, the equivalent carbon intensity becomes very low. So your carbon intensity of your heating, so this is grams of CO2 per kilowatt hour of heat input into the house becomes, or the building becomes very low. And increasingly, data center providers are thinking about this as well. So Green Pixie is a company I've been working with recently who are looking at how to monitor the carbon emissions of processing tasks. And so you might make decisions about where you run your tasks or what time you run your data processing tasks to minimize the carbon emissions from that computation. As I said, the home heating area is kind of interesting, and it's kind of challenging for a lot of AI research because we have the potential of having lots and lots of data. So these smart meters, there are 30,000 homes in the UK. So potentially you get live data from 30,000 homes. So that would seem to be a very sort of data-rich environment, and it would seem to be a very compelling domain if you wanted to apply machine learning or AI in this setting. But the challenge is typically that you don't have a lot of ground truth. So you have a lot of live data. Getting that data is a little bit sort of restricted because you have to go through the energy retailers. You can't access it particularly easily. The energy retailers have access to data from their customers and only their customers, which makes it challenging to do learning at this sort of scale. But typically the real challenge is there's very little ground truth, and collecting ground truth is really expensive because you typically have to go into people's homes and understand how they're actually using their heating and using their appliances before you can sort of do any training. So we've did a couple of projects to try and address this. So one of them was sort of quite simple, just sort of building a very simple device to try and collect temperature data from people's homes. When we started to think about sort of smart heating, it was very clear that there wasn't even data sets for how do people use their heating systems. And in order to get that, you need to have homes with smart heating systems installed, and not very many homes at the time or still have those installed. So what we developed was a very simple temperature logger. So this was a temperature logger that we sort of mail out to people who volunteered. The idea is that you'd sit it on top of your thermostat and you would measure the temperature at the thermostat for a week. So this would, if you had a smart thermostat, the smart thermostat company would have access to this data. But many people just have these very traditional, very simple thermostats controlling a gas boiler. And so the idea was that you just sort of put the temperature logger on the top of the thermostat. And so we don't really know what the home is doing, the rest of the house. We only have this measurement at one point. But crucially, that's the only thing that the heating system sees as well. So the heating system doesn't know how warm it is in your living room. It only knows how warm it is in the hallway. And often these radiators are very poorly placed. They're sort of sitting above a radiator. And so they don't really heat the house at all. So one of the things we started to do was look at where can we incentivize people to give us this data. And the incentive for doing that was to sort of provide some analysis of people's homes. So we sort of launched this system, and very quickly we could sort of deploy it into about sort of 2,000 homes. We built a small number of these, about 100 of these devices, and then sort of had a mail-out system to recycle it. And actually, that was sort of quite a big lesson from the project, that actually mailing out sensors that people can deploy at home is a very effective way for a small research team to sort of scale up research. The cost of going installing things in in people's homes is very high. If you've got people, postdocs who have to sort of go out and interact with people, but if you can post them out and people can install it themselves, it becomes very efficient. And we started to do some sort of simple analysis that we could do, that we could bootstrap without seeing any previous data. And so we started doing sort of very simple sort of model-based things. Could we spot the decay of temperature when the heating system goes off, and try and quantify that? And these very simple metrics turned out to be really interesting. People were quite surprised. You go to bed in the evening, typically your heating system switches off, and you have no idea what your house does. How cold does it get? And you have no comparator. Is your house getting colder than anyone else's house? Even is your thermostat higher than anyone else's house? And there are all sorts of cultural patterns. So we deployed in student homes as well, and we found that sort of some people would have the heating on at night, so the heating would be off in the day and the heating would be on at night. And that was kind of surprising because all the thermostat manufacturers we'd spoken to were convinced that everyone had this sort of very traditional pattern, and everyone would sort of switch off the heating at night. But that's not necessarily true. A lot of people had the heating on all the time, just completely flat, which isn't a bad strategy as long as your home is well insulated. But if your home isn't particularly well insulated, that can be very expensive. So we built a simple sort of thermal model of the home that we could sort of characterize with these measurements. And then we could do this sort of modeling and say, okay, well, how much energy would you save if you reduced your energy, your thermostat setting by 1 degree? And it turns out you can do quite a lot of modeling, but you do get back to this sort of quite good benchmark figure in the UK, which is sort of 10%. So sitting behind this is quite a sophisticated thermal model of the home that we parameterized with what we think the home is doing, and you do end up with this sort of metric of 10%. So one of the sort of it's kind of positive and negative at the same time is that a lot of the insight you get from studying heating systems is that you should insulate the home and turn the thermostat down. And if you kind of think about the problem before you start, that's probably the advice that you might have anyway. So a lot of the sort of the optimization is kind of around the edges. And the key thing is that before you even start optimizing energy use, you need to insulate the homes well, and you need to think about what thermostat setting you're actually going to use. So this turned out to be sort of quite successful, and it was bought by a company called QB, who kind of used it as a first stage for discussing with customers about installing smarter heating systems. So it's quite a hard sell to say, we will come in and rip out your heating system and put this smart system in. But actually, if you can get some initial data, you can then have a sort of a fact-based discussion with the customer, sort of saying, okay, well, your home is actually one of the worst performing homes in terms of thermal efficiency, and if we did this, you would save X amount. So these simple interventions to collect some data allow you to collect some ground truth that allow you to build the models, and then those models can be very useful even if they're not apparently particularly sophisticated. So the challenge with this project is that we only have temperature data. We don't have the consumption data, so we don't see the amount of gas or electricity that's being used by the home. And so we recently did a project with EDF Energy, which is kind of on the other side of this challenge. And that's basically to try and make use of smart meter data to infer something about the home. And so this is kind of the opposite extreme. That in that sense, we have the energy consumption data, but we don't know anything about the temperatures inside the homes. We might have that if they have a smart thermostat, but most people don't have a smart thermostat. So this was a project run by the government to try and use smart meter data to replace the energy performance certificates. So if you rented a home or you've sold a home, you know that you have to get this energy performance certificate. And this is kind of it seems like a survey, physical survey, but it's kind of a physical survey where you sort of tick a few boxes and you give the dimensions, and that informs a calculation of the energy efficiency of the home. So there's no actual ground truth of how energy efficient is this home. It's basically a quantified a model, which is basically based on the size of the home and some characteristics about what sort of heating system it has, what sort of walls it has. So the ground truth for those energy performance certificates is really expensive to collect. You basically have to perform a test where you seal up the home and you measure how quickly it leaks heat. So that's a very sort of expensive process to go and actually sort of ground truth these energy performance certificates. And it turns out that if you do that ground truthing, the energy performance certificates don't actually turn out to be particularly accurate. And there are lots of cases where the dimensions have been input in the wrong units, and so the estimation is sort of is way out from reality. So this was a government project to try and use smart meter data to replace these certificates. Can we do a measurement-based process? And so some of the projects in here would install additional sensors, but we wanted to do it just with absolutely minimum data. And so the minimum data that we have is just the energy consumption per day. Okay, so this is from those smart meters. If you have a smart meter, you might be able to sign in to a 30-minute measurement option, but the default case is the energy retailer gets your daily energy consumption. So that's the energy retailer gets that from every single home. And so this is some sort of synthetic data to sort of illustrate the process. And so what you get is this very, very noisy daily energy consumption. And if you have that data over a year, you can sort of see there's some sort of clear correlations with external temperature, but the data is kind of quite noisy. But what you can do is you can sort of plot the daily energy consumption against the external temperature, and suddenly you sort of see a lot of patterns in this data. And so you can sort of see here, this is the case where out here the heating system is off. The temperature is quite high, so the heating system is off. And so this is kind of like the baseline consumption of the house. There's a few days here where it's actually really cold, but there's still this sort of baseline consumption. So in this case, the heating system doesn't seem to be on. And then you get this sort of very clear linear bit here, where this is leakage from the home. And so the leakage from the home is kind of proportional to the difference between the internal temperature and the outside temperature. And the home is kind of roughly in thermal equilibrium. So you have to put the same amount of energy in each day as leaks out. So this turns out that you can generate these plots, and then we apply a sort of a Bayesian linear regression to try and automatically find this line, automatically find this line, automatically remove all the strange anomalies, and then it becomes a process of a model-based process of trying to make this model of home energy performance more and more complex, and adding in all the complexities. So suddenly you see people with electric cars, which are sort of huge additional loads. You see people with local solar generation, which isn't visible to the grid. Typically, if you're doing some local generation, the retailer doesn't see that at all. They just see the net consumption of the home. So you can build in all these sort of extra complexities, but you're kind of forced to use a model-based sort of Bayesian inference approach, because you don't have ground truth. You basically have to have a prior model and refine that prior model by looking at the data to try and sort of understand what's actually happening in this home, because collecting ground truth is incredibly expensive. So this project sort of was finished about a year ago, and they actually did a survey of about 30 homes and actually did this energy performance certificate test. And this model-based approach, which doesn't use a huge amount of data, actually turned out to be one of the best. And it was just as good as actually putting in temperature sensors into the home. So for anyone who's sort of interested in AI, we hear an awful lot about machine learning and neural network-based approaches, but there is still a case for maybe sort of more traditional probabilistic machine learning, where we don't have training data. We just have sort of a good physical understanding of the process, and then a small amount of data. And what we have to do is try and fit that data using sort of robust approaches that are going to handle all the anomalies that we might see in the real world. So I'll leave it at that. So that's there's a lot of work to do in AI for heating, and I think it will become an increasingly important application domain as we finally get these smart homes and the heat pumps installed in people's homes. Okay, thank you.
Okay, that's great. Thanks very much, Alex. So do we have questions from the room? Yes.
First of all, thank you for by turning around on the question, how unsustainable the current AI paradigm is. So, you showed very well how from the processing is now 1 billion times more efficient, but maybe we can look at how efficient the human brain is. And you mentioned data centers, for example, and how much power is needed for the CPUs, GPUs for the current AI paradigm. So in a way, AI helps us for sustainability, but at the same time, the current AI paradigm is not sustainable. Do you have any comments on that?
Yeah, so I think if you're, so it depends on what AI you're doing. So AI typically now means sort of large neural networks, and certainly that's the case. A lot of the neural network research I do is targeting very small microcontrollers, and then when you're training, your desktop is easily fast enough to do the training because the model is actually going to run on such a small processor that you already have this sort of 100-fold performance increase on your desktop. But it's definitely a case, and I think the people in data processing are becoming much more aware of carbon intensity, and you can sort of see that if you're going to be a large consumer, buying solar power or situating your data center where there is solar power would seem to be sort of appropriate. There is sort of question that comes up a little bit with crypto mining, where crypto mining people do that, but you kind of think, well, if they weren't there, then that power would be available to the rest of the grid. So the fact that you're consuming low carbon energy for a pointless task doesn't really absolve you of the fact that that power would be better used elsewhere. So I think if you're working in these very large models, then it becomes something that you really do have to worry about, and certainly in just in just the cost. The cost of training the models comes down to these huge energy costs. So it's definitely a challenge, yeah.
Just wanted to check, do we have any questions online? No questions online. Any more questions from the room?
Thank you so much, Alex, for your great presentation, very insightful. I'm just wondering about many ideas that you just provide here. And one thing that I was actually thinking on was about, have you ever thought about developing some sort of recommender system so that you could personally advise people on the best way to use their thermostats and energy and etc., so that this possible AI model, recommender system, AI powered model would enable people to get better decision making process into their homes, but also for industry, for business centers and etc.
Yeah. So the heating, heating systems are really interesting because it's such, to the engineers, it's seen as such a simple system, but actually to the user, it's actually quite complex and opaque. And there's this sort of famous thing around sort of the mental model of how a thermostat works. If you turn it up higher, does it get warmer faster? And there's sort of two mental models that you can have about how this system works. And then you have a home with individual radiator thermostats, and it becomes hugely more complex. So in Southampton, I had a student who was in human factors, and she built like a home simulator. And you would sort of say, okay, well, here's your new home. Can you set it up so that it warms up to 20 degrees during these hours and then goes off at night? And actually, in that simulator, having access to all those radiator valves just becomes so complicated that no one can really sort of control the system. So it kind of does point to the idea that once you've got that individual room-based control, it's then too complex for someone to individually set up, and you kind of want, either you want to automate it, or you want some sort of setup wizard that will tell you all the settings, and then maybe monitor the system and tell you how to sort of tweak those settings. So there's definitely a case for not quite full automation, but actually some AI assistance to help you set up this system and to monitor it and to keep it working. And I think that's probably sort of quite valuable because it's easy to imagine that everyone will replace their heating systems, but most technology in the home takes a huge amount of time to seep in and to be widely deployed. no, the smartphones, most people have had 5 or 6 smartphones in the time that their smart meter has finally been installed, and that smart meter will be in the house for like 25 years. So that's not where you want the intelligence to be.
Okay, thank you. So I know there are going to be more questions, but in order to give time for coffee, what I suggest is take questions over coffee, and then we'll come back for the next session. So thanks very much again, Alex Rogers. Thank you. And